All the neural networks that we've seen so far work with numbers. That's because the input to a neural network has to be in numeric form. But we've spoken of using neural networks for sentiment analysis, which is essentially a text problem. So, how do we use neural networks with text? One of the problems that we are going to solve using recurrent neural networks in this section is the problem of sentiment analysis. Now, if you think about sentiment analysis, it's basically a text classification problem. You want to classify reviews as positive or negative. RNNs tend to be your neural network of choice when you're working with text because if you think about it, text is essentially sequential data. They're a sequence of words one after the other, and you'll find that RNNs are great at learning sequential data because RNNs understand special time relationships. Here are some real world examples where we choose to use RNNs with text data. Let's say you want to predict the next word in a sequence. This is true for autocomplete problems, whether you're typing into a search engine or anywhere else. You'd say something like, the tallest building in the world is, and you should be able to predict the Burj Khalifa, at least at this point in time. RNNs are also extensively used in language translations. It accepts an input sequence of words in a language such as English and it'll translate it to the corresponding words in another language, let's say French. And of course, RNNs are very popular for sentiment analysis and natural language processing. Let's say you have a complicated sentence like this is not the worst restaurant, not by a long way. RNNs will be able to parse the exact sequence of words and figure out that this is actually a positive or a neutral review. It's not really negative, even though we have the word worst in there. All right, I've made the case for text being sequential data, and we know recurrent neural networks are great with sequential data. So let's go ahead and use one. But you'll immediately run into a problem. You're quite familiar with neural networks by now, and you know that neural networks train weights and biases and they accept numeric input. But text is text, it's not really numbers. So, how would you use text as an input into a recurrent neural network? One way is to just take a bunch of characters or words and assign numbers to it, but that isn't really meaningful. What we are really looking for is to represent text as numbers in a meaningful manner, where somehow the numbers which represent a word have some semantic connections and relationships with other words. Now it turns out that this is a problem statement that stands alone, and in fact, this is a problem statement that can be solved using a neural network. We'll come to that in a little bit. Now, let's go on and understand how we can represent text as numbers meaningfully. In order to get there, you first need to imagine the document as a word sequence. Here, D represents the document, and a document is essentially a tensor of word encodings. We'll get to this tensor of word encodings in a step by step manner. The first thing is text as sequential data. This is something that we are aware of, and this is something that's familiar to us. We can model a document as an ordered sequence of words. The document contains words in a certain order, as you can see from the example on screen. This is not the worst restaurant in the metropolis, not by a long way. The exact order in which the words appear in this document is meaningful. So, when you split the document into words, you can then express this in some ordered form. What we are actually doing when we split a document into words is tokenizing our document in order to feed into a recurrent neural network. Here, the word this is our very first word represented by W0, and it can be encoded into some form that is X0. So, W0 represents the actual word, that is the text form, and X0 is some numeric encoding. You can do this for every word in the document all the way through to the n words that are actually present in this document. Every word has a corresponding text and some numeric encoding of the word. Once you have this numeric encoding, you can represent this document as a tensor. This tensor is basically just a list of these encodings. Remember that every encoding has a numeric form. Neural networks can just deal with numbers after all. Now, our problem statement is a little different. The big question here is, How can words be represented as numeric data? What is the best possible form for words to be expressed in numbers? Because once we have those numbers which represent words, we know how we can construct a document from those numbers and represent the document as a numeric tensor. There are several methods and algorithms that we can use in order to represent words in numeric form. These words in numeric forms are typically called text embeddings, and that's how we'll refer to it at the rest of this lecture. We'll study three methods in detail. The first is the one hot representation. This is something that you're familiar with. Another method is the TF-IDF form. TF stands for term frequency and IDF stands for inverse document frequency. And the last and most popular method, this is the method that's commonly used with machine learning models built using neural networks, is word embeddings. Neural networks can only work with numeric input that is established, that cannot be changed. What we need to do to use neural networks for sentiment analysis, natural language processing, and other problem statements which involve text is to have some way to represent your text data in numeric form. If you think of a document as a sequence of words, what we need to do is to encode every word as some kind of number. And there exist several different algorithms and methods which allow you to do this. A few examples are the one hot notation, the TF-IDF algorithm, and word embeddings.